Close your eyes and listen. Can you hear it? The gentle tick of time moving around you, through you, carrying you forward on its invisible current. Time is perhaps the most mysterious companion of our lives, always present, never seen, flowing, like an endless river that touches everything yet belongs to no one. Tonight, as you settle into the soft embrace of your pillow, we're going to explore one of the most beautiful secrets hidden in plain sight. It's a secret that lives in your pocket, travels with you everywhere, and connects you to the farthest reaches of space. Your smartphone, that familiar rectangle of glass and metal holes within it, a conversation with Einstein's most profound discoveries about the nature of time itself. But let's begin simply with the feeling of time as it moves through this moment. Feel your breath rising and falling, each inhale and exhale marking the passage of seconds. Your heart beats steadily, a biological clock that has been keeping time since before you were born. These rhythms of your body are your most intimate relationship with time's passage. Time seems so constant, so reliable. The second hand of a clock moves with mechanical precision. Digital displays change their numbers in perfect intervals. We schedule our lives around time's apparent regularity, meeting friends at precise moments, catching trains that arrive exactly when promised, coordinating our complex human dance through shared agreements about when things happen. Yet time holds secrets that would have seemed like magic to our ancestors. Deep in the quantum realm, time behaves in ways that challenge everything our everyday experience tells us. At the grandest scales of the universe, time stretches and compresses like a cosmic accordion, playing melodies we're only beginning to understand. Your smartphone participates in this cosmic symphony every time you ask it for directions. When you touch that little blue dot that represents your location on the screen, you're witnessing the culmination of humanity's greatest insights about time, space, and the fundamental nature of reality. That simple act of finding yourself on a map as a conversation between your device and satellites orbiting high above Earth, a conversation that depends entirely on understanding how time behaves differently in different places. But how can time behave differently? The question sounds almost absurd. Doesn't a second last exactly 1 second, everywhere and always? This is what humans believed for thousands of years, and it seems to match our daily experience perfectly. The clock on your nightstand ticks at the same rate as clocks around the world. Time appears to be universal, absolute, unchanging. This seemingly obvious truth about time, that it flows uniformly everywhere, forms the foundation of our intuitive understanding of the world. We imagine time as a vast cosmic metronome, keeping perfect rhythm for the entire universe. In this picture, every star, every planet, every particle of matter moves through time at exactly the same rate. Time becomes the universal backdrop against which all events unfold. But what if this fundamental assumption about time is wrong? What if time isn't the fixed, universal constant we imagine it to be? What if time itself can speed up, slow down, stretch, and compress depending on where you are and how fast you're moving? These questions aren't just philosophical puzzles, they have practical, everyday importance. The GPS satellites that help your phone determine your location, racing through space at tremendous speeds, experiencing time differently than you do here on Earth's surface. Without accounting for these differences in time's flow, your GPS would be off by miles within just a few hours. The familiar magic of navigation depends entirely on understanding time's hidden flexibility. Tonight, we'll journey together through this landscape of time's mysteries. We'll discover how a young patent clerk, Albert Einstein, gazing out his office window in Switzerland, came to understand that time and space are woven together in ways that transform our understanding of reality itself. We'll explore how this understanding enables tiny devices to have conversations with satellites 20,000 kilometers above Earth, translating their time-dilated messages into the familiar blue dot that shows your location. As you rest here, feeling time's gentle passage in your breathing and heartbeat, Imagine that you're already part of this cosmic conversation. The atoms in your body, the electromagnetic fields around you, the very space you occupy, all of these participate in time's strange dance. You're not separate from these mysteries. You're embedded within them, a conscious observer of time's flow who has the remarkable ability to contemplate the nature of time itself. This is where our journey begins, with the recognition that time is not what it seems. The steady, reliable ticking of clocks masks a deeper reality where time proves to be flexible, relative, and beautifully strange. Your everyday experience of time, the way seconds follow one another in orderly succession, is just one perspective on a phenomenon far richer and more mysterious than our ancestors ever imagined. Feel yourself settling deeper into this contemplation. Time surrounds you like an invisible ocean, and tonight, we're going to learn to swim in its currents. We'll discover how understanding time's true nature allows us to perform everyday miracles like finding our way home, hearing signals from space, or coordinating the complex technological systems that connect our modern world. The journey ahead will take us from the smallest scales of atomic clocks to the vastest reaches of space, from the practical workings of satellites to the deepest philosophical questions about the nature of reality itself. Each step will reveal new layers of wonder hidden within the familiar experience of time's passage, but all of this exploration starts with a simple recognition that time, this invisible companion that shapes every moment of our lives, holds secrets that are both beautiful and strange. As we prepare to dive deeper into these mysteries, rest in the knowledge that you're about to discover how Einstein's most abstract insights translate into the most practical aspects of modern life. Picture a quiet office in Bern, Switzerland. In the year 1905, sunlight streams through tall windows, illuminating dust motes that dance in the warm air. At a wooden desk sits a young man with unruly hair and thoughtful eyes, surrounded by patent applications for electrical devices and mechanical inventions. His name is Albert Einstein, and though he spends his days evaluating other people's ideas, his mind wanders to questions that will transform our understanding of the universe itself. Einstein is 26 years old, recently married, and working 6 days a week as a technical expert in the Swiss Patent Office. His job requires him to understand how things work, to see through complex descriptions, and determine whether new inventions are truly novel. But in the quiet moments between patent reviews, his thoughts drift to deeper puzzles that have fascinated him since childhood. He thinks about light. What would it be like to ride alongside a beam of light racing through space? This question had haunted him since he was 16, when he first imagined chasing after light at the speed of light itself. Would the light beam appear to stand still relative to him? Would he see the electromagnetic waves frozen in space like a photograph of motion? These weren't idle daydreams. Einstein possessed an unusual gift for what he called thought experiments, imaginary scenarios that revealed deep truths about reality. While other physicists filled blackboards with complex equations, Einstein preferred to think in pictures, to imagine himself as a participant in the phenomena. He wanted to understand as he gazes out his office window, watching people walk past. On the cobblestone streets below, Einstein contemplates the nature of motion itself. Those pedestrians appear to move at different speeds depending on his perspective. A person walking might seem slow compared to a passing carriage, but fast compared to someone sitting on a bench. Motion, Einstein realizes, is always relative. It depends entirely on your point of view, but light behaves differently than anything else. Experiments have shown that light always travels at the same speed, roughly 300 million meters per second, regardless of how fast you're moving when you measure it. This seems impossible according to everyday logic. If you're running towards someone throwing a ball, the ball appears to approach you faster than if you were standing still. But light doesn't follow this rule. Whether you're moving toward a source of light or away from it, light always approaches you at exactly the same speed. This unchanging speed of light creates a puzzle that keeps Einstein awake at night. If light's speed never changes, then something else must be flexible to accommodate this constancy. But what could be flexible enough to bend around light's unwavering pace? The answer comes to him in a flash of inspiration, but through months of careful thinking about the relationship between space and time, Einstein begins to realize that our intuitive understanding of time as a universal, absolute backdrop against which all events unfold must be wrong. Time itself must be relative, just like motion. Imagine you're standing on a train platform, watching a train approach. From your perspective on the platform, events inside the moving train appear to happen more slowly than events around you. A passenger's watch ticks more slowly than yours. Their movements seem slightly sluggish. Time itself flows differently for the person on the train than it does for you standing still. This effect is incredibly tiny at the speeds of everyday life, so small that you would never notice it, but as speeds approach the speed of light, the effect becomes dramatic. Time doesn't just slow down slightly, it can slow down enormously, stretching seconds into minutes, minutes into hours. Einstein's insight goes even deeper. Not only does time flow differently for objects moving at different speeds, but gravity also affects time's passage. Imagine time as honey flowing down a hillside. In regions of strong gravity near massive objects like planets or stars, time flows more slowly, like honey moving through a narrow passage. In regions of weak gravity, far from massive objects, time flows more quickly, like honey spreading freely across a wide surface. These ideas seem to contradict everything our senses tell us about the world. Time feels absolutely uniform. We never notice it speeding up or slowing down based on our motion or location. But Einstein realizes that our everyday experience represents just one narrow slice of reality's full spectrum. At the speeds and in the gravitational environments where humans typically live, time's flexibility remains hidden beneath an appearance of constancy. Yet this flexibility has profound implications. If time truly behaves this way, then our entire understanding of simultaneity, of what it means for two events to happen at the same time, must be reconsidered. Events that appear simultaneous from one perspective might occur at different times when viewed from another moving reference frame. Einstein publishes these ideas in 1905 in a paper with the modest title On the Electrodynamics of Moving Bodies. The scientific community initially responds with skepticism. These concepts seem too strange, too far removed from everyday experience to represent reality. How can time be relative? How can motion through space affect the passage of time itself? But Einstein's mathematics is elegant and precise, and his theory makes specific, testable predictions. If time truly dilates at high speeds and in strong gravitational fields, then these effects should be measurable with sufficiently sensitive instruments. The theory stands ready to be proved or disproved by experiment. As Einstein continues his work in the patent office, carefully reviewing applications for new inventions, he has no way of knowing that his insights about time's flexibility will someday become essential to technologies that transform human civilization. He cannot imagine that invisible satellites will someday circle Earth, their atomic clocks ticking at slightly different rates than clocks on the planet's surface, requiring constant adjustments based on his understanding of time's relativity. The young patent clerk, gazing thoughtfully out his office window at the streets of Bern, has discovered something profound. Time is not the absolute, unchanging backdrop we imagine it to be. Time is woven into the fabric of space itself, creating a dynamic, flexible medium that responds to motion and gravity in ways that will revolutionize our understanding of reality. But understanding time's flexibility is only the beginning of our story. High above Earth, at this very moment, metal guardians circle our planet in precise formation, their journeys through space creating exactly the kinds of time distortions Einstein first imagined in his quiet office more than a century ago. You sit quietly in a room you've never seen before, yet it feels oddly familiar. The warm scent of old paper, the gentle ticking of a clock on the wall, and sunlight slanting through tall windows. This is Bern, Switzerland, in the early 1900s, outside. The world moves forward on train tracks and telegrams, but inside this modest patent office, time begins to dissolve. At a desk near the window sits a man with unruly hair and a distant look in his eyes. Albert Einstein. He stamps documents and reviews inventions, but his mind is elsewhere, skipping between equations and imagined journeys at the speed of light. He's only in his 20s. He has no university post, no laboratory. Just a curious mind, a worn notebook, and a quiet obsession with how the world really works. You settle beside him in thought. The two of you share the same question. What does light do? Not just in a physical sense, but in a deeper, more mysterious way. If you could ride a beam of light, what would you see? What would happen to the ticking of clocks, the rhythm of your breath, the distance between stars? Einstein asks these questions not like a scientist in a lab, but like a child watching raindrops race down glass. He knows the equations of Newton. He knows that, under classical physics, time is universal and absolute, ticking the same for everyone, everywhere. But something in him whispers that this is not quite right. The equations of electricity and magnetism, Maxwell's equations, seem to hint at a different truth, a conflict, a contradiction. He begins with light. Light is strange. It always moves at the same speed, no matter how fast you move toward it or away from it. It doesn't follow the rules of intuition. This constancy of light is like a stubborn thread, tugging at the seams of the old worldview. And so Einstein, in the stillness of his small office, begins to tug back. You imagine yourself now on a train, a smooth, quiet ride across the countryside. A clock sits on the wall beside you. It ticks steadily. You glance out the window and see another clock, fixed to a pole beside the tracks. The train speeds by. From your seat, both clocks seem in harmony. But from the platform, watching you pass, things are different. The light from your clock has to chase after you. The observer on the platform sees the tick, just a little later. Einstein follows this idea into a world where time is no longer fixed, where simultaneity, the idea that two things can happen at the same time, becomes slippery. Events once considered absolute start to depend on where you are and how fast you're moving. It's a radical idea, but it flows calmly and logically from the constancy of light. If light never changes speed, if it always races ahead at 299,792 kilometers per second, then time must bend. It must stretch and shrink to make space for that unwavering brightness. You float through these thoughts as though drifting in warm water. Einstein's quiet revolution is not about noise or confrontation. It's about harmony, aligning the rules of reality with the strange behavior of light. From his thought experiments, he begins to sketch out what he calls the special theory of relativity. In this theory, time and space are no longer separate. They are one fabric, woven together, curving gently around mass and motion. The faster you move, the slower your clock ticks. The closer you approach the speed of light, the more reality tilts. These are not just dreams. Years later, his predictions would be tested, and they would hold. Astronauts, flying high above Earth, would age differently than those who remain on the ground. Atomic clocks flown on planes would fall out of sync with those left behind. The universe, it turns out, is more flexible than we thought, and yet, there is a strange serenity in this flexibility. You are not losing time, you are experiencing it relative to your motion, your frame of reference, your unique path through space. Time becomes not a fixed river, but a personal stream. In the office, the sunlight is shifted, dust motes swirl in lazy spirals. Einstein sits back, the corners of his mouth gently lifting. He does not seek approval. He does not rush to publish. For now, he is simply satisfied that the world makes a little more sense. You wander further into this new landscape, a place where space itself is not a rigid stage, but a participant in the drama of existence. The distance between two stars depends on how you measure it, on how fast you are traveling. Even the shape of reality bends, ever so slightly, under gravity's hand. This chapter of thought, the special theory of relativity, is only the beginning. In time, Einstein will see deeper. He will realize that acceleration and gravity are siblings, and that space can curve like a soft blanket beneath a weight. But for now, this quiet revolution is enough. You notice that the clock on the wall still ticks, but it seems quieter now, softer, as if aware that its authority has been gently dethroned. Time, you realize, is no longer a master. It is a partner, adaptable and elegant, a rhythm that dances with motion and light. And so, in the hush of that dusty room, a young man's dream reshapes the world, not with thunder, but with thought, not with force, but with clarity. You leave the office carrying something new, a sense that reality is not fixed, but responsive, not rigid, but relational. The stars beyond the window seem to shimmer a little more freely now. Their light reaches you not just across distance, but across time. You feel, somewhere deep inside, that every second is more mysterious than it seems, every moment a little more alive. Outside, the sun sets, the shadows lengthen, and you wonder. Night deepens, and while you sleep, the sky becomes a ballroom. Above you, 20,000 kilometers high, dozens of satellites glide in synchronized paths, not with flash or fanfare, but with the quiet grace of a well-rehearsed dance. Their names are unfamiliar, their forms barely visible, but their work is everywhere. They do not shine like stars, nor drift like clouds. Instead, they orbit, fast, precise, tireless. Each one traces a circle around Earth, looping once every 12 hours, locked into a rhythm only the cosmos and a few minds truly understand. These are the satellites of the Global Positioning System, the GPS constellation, not just tools for maps or navigation, but floating instruments of astonishing precision. Inside each one beats an atomic heart. You might imagine something loud, humming, or mechanical, but no, these clocks are not like ticking watches or whirring gears. Their sound, if you could hear it, would be closer to the whisper of electrons changing states, the shimmer of cesium or rubidium atoms vibrating in perfect rhythm. An atomic clock does not guess the time. It doesn't need winding. It listens to the natural frequency of atoms, the purest, most stable pulses in the universe. Each beat is a promise kept. This moment is now. This second is true. Why does that matter? You wonder. Because time is everything. Your phone knows where you are because it knows when you are. Imagine this. You're standing still on a quiet path. Above you, for satellites reach out, each sending a signal, a note in a silent harmony. Your receiver listens. It measures how long each note took to arrive. If time were even a fraction off, if the clocks on those satellites were slow, by a millionth of a second, your location would be wrong by hundreds of meters. But they are not off, they are not late. They sing together, perfectly in tune, and yet, even perfection must be corrected. Because something invisible leans against their rhythm, something Einstein once glimpsed from a dusty room. You remember, don't you? Time bends. It moves differently depending on how fast you travel, and how deeply you fall into gravity's embrace. Satellites, moving quickly and orbiting high above Earth, experience both. They move fast enough that time slows for them ever so slightly, a whisper of special relativity. But they are also far from Earth's gravity, where time speeds up, a quiet hum from general relativity. The result: their clocks tick faster than those on Earth by about 38 microseconds per day. Not much, you think. Less than a blink, but if left uncorrected, that tiny difference would grow. And within minutes, your phone would be lost in space. So scientists adjust. They program satellites to account for this gentle tug of time. Before they even launch, the clocks are set to tick a bit slower, so that in orbit, After gravity and velocity have whispered their changes, the rhythm returns to true. This is the dance, a partnership between physics and engineering, between unseen equations and everyday lives. You, walking along a beach, or driving through mountains, or finding your way home, are connected to a network of stars we built ourselves. But it's not just position you're receiving. You're receiving time, carved into signal, shaped by speed, sculpted by gravity. Every moment you glance at your clock, somewhere above, a satellite has sung the notes that made it possible. There's beauty in this, quiet and deep, that we must understand the universe, or not only the big and the bold, but the subtle and the small. In order to move safely through it, you're part of this system, even as you sleep. The signal reaches through your walls, through your dreams, brushing gently past trees and towers and clouds, until it finds you. It tells your phone where you are. It tells time itself where you are. In this way, physics becomes personal. Not just stars and planets, but your footsteps, your travels, your days, and yet, this precision is fragile. A satellite struck by space, debris, a solar flare disrupting signals, a slight drift in atomic rhythm. Any of these could tilt the dance. So we tend it, we recalibrate, we synchronize, we guard the constellation above with care. Still, it humbles us, because this system only works if we understand time, truly understand it, not as a straight line, but as a shape that can curve. It works because Einstein's insight, that time is not absolute, but relative, turned from theory into practice, because those strange shifts in seconds, those tiny bends in rhythm, are real. And if we did not listen to them, we would be lost. You lie still now, somewhere beneath the circling satellites. You cannot see them, but they are there, quiet sentinels, floating on invisible rails. Their pulses pass through you, guiding ships across oceans, planes across skies, and thoughts across vast digital networks. And as they glide, they remind us, even machines must dance with time. Close your eyes and imagine the smallest clock in the universe, not the tiny watch on your wrist, not the delicate mechanisms of an antique timepiece, but something far more intimate and precise. Deep within each GPS satellite, 20,000 kilometers above your sleeping form, lives a clock made not of gears or springs, but of atoms themselves. These are cesium atoms, silver white and luminous in their microscopic beauty. Picture them floating in their chambers, like tiny dancers, each one vibrating with an energy so pure and consistent that it puts every human-made timekeeper to shame. Each cesium atom beats its rhythm 9 billion times every single second, creating a pulse so regular that if you started counting from the moment of your birth, this atomic heartbeat would not have gained or lost even one beat by the time you become very old. You rest here in your bed, your own heart beating perhaps 60 times each minute, steady and reassuring in your chest. But high above you, these atomic hearts beat billions of times faster, their rhythm so precise that they measure time itself. They are the universe's most faithful metronomes, keeping perfect time not just for minutes or hours, but for the cosmic dance of planets and the gentle journey of light across space. In the quiet darkness of space, inside chambers no larger than your closed fist, these cesium atoms exist in a state of perfect isolation. They float suspended in magnetic fields, untouched by gravity's pull, unbothered by temperature changes that would make ordinary clocks run fast or slow. Here, in this pristine environment, they can express their truest nature, their pure, unwavering oscillation that has become humanity's definition of time itself. Think of how a tuning fork, when struck, creates a perfect note that resonates through the air. The cesium atom is like nature's tuning fork, but instead of sound, it creates time. When energy touches these atoms, in just the right way, they respond with a frequency so exact that scientists have used it to redefine what we mean when we say 1 second. A second is no longer defined by the rotation of our Earth or the swing of a pendulum, but by the atomic dance of cesium 9 billion, 192 million, 631,770 oscillations. As you lie here breathing slowly, your lungs filling and emptying in their gentle rhythm, imagine the quantum world inside these atomic clocks. Electrons orbit their nuclei in perfect shells, like planets around microscopic suns. But unlike the planets in our solar system, these electrons can only exist in specific energy levels, like invisible steps on a cosmic staircase. When they jump from one step to another, they release or absorb energy with mathematical precision. This is where the magic of atomic timekeeping reveals itself. When cesium atoms are bathed in microwave radiation of exactly the right frequency, their electrons perform a synchronized dance, jumping between energy levels in perfect unison. It's as if millions of microscopic ballerinas suddenly move together, responding to music that only they can hear. This transition creates the atomic clock's reference signal. Its heartbeat that never varies, never grows tired, never loses its perfect rhythm. The engineers who built these clocks understood something profound about the nature of reality itself. Time, they realized, is not just a human invention or a ticking on a wall. Time is woven into the fabric of atoms, written in the language of quantum mechanics, expressed through the eternal dance of particles, too small to see, but too precise to ignore. Each GPS satellite carries not just one, but several of these atomic clocks, like a choir of atomic voices, singing in perfect harmony. They sing together, their frequencies compared and measured, ensuring that even if one clock should somehow falter, the others continue their flawless performance. This redundancy creates a reliability that borders on the miraculous. These clocks are so accurate that they would lose less than 1 second if they ran for millions of years. But why does this precision matter for something as simple as finding your way home? Because GPS doesn't just tell you where you are. It tells you where you are by measuring the time it takes for signals to travel from space to your device. Light travels fast, impossibly fast, but even light takes time to journey from satellite to Earth. To measure your position accurately, the system must know exactly when each signal was sent and exactly when it arrives. If these atomic clocks were off by even 1,000th of a second, your GPS would place you kilometers away from your true location. You might think you're in your bedroom when the system says you're standing in a field miles away. The precision of cesium atoms ensures that when you ask your phone to guide you home, it can point you to your front door, not just your neighborhood dot in the stillness of your room. As your breathing grows slower and deeper, consider the hidden symphony playing out above you. Billions of atomic oscillations each second, multiplied by the dozens of satellites overhead, creating a rhythm more complex and beautiful than any music ever composed. These tiny timekeepers, no larger than molecules, are the foundation upon which our modern world's navigation depends. Tomorrow, when you wake and perhaps use your phone to find a new restaurant or navigate to a friend's house, you'll be relying on the faithful heartbeat of atoms you'll never see, in satellites you'll never visit, keeping time with a precision that would have seemed like magic to every generation that came before us. The cesium atoms continue their eternal dance, measuring out the seconds of the universe with perfect dedication. Their rhythm connects the quantum world to the cosmic scale, bridging the gap between the infinitely small and the magnificently large. And as their atomic heartbeat marks time in the darkness of space, it reminds us that precision and beauty often exist in places we never think to look. But even these perfect timekeepers face a challenge that Einstein predicted long ago. As they race through space at tremendous speeds, time itself begins to behave in ways that would have puzzled every clockmaker in history. You rest motionless in your bed, but high above you, GPS satellites are racing through space at speeds that would take your breath away. Each satellite moves at nearly 14,000 kilometers per hour, circling our entire planet twice each day. To put this in perspective, if you could travel at their speed, you could fly from your home to any city on Earth in less than 2 hours. They are cosmic race cars, forever running a track that circles the globe. But something extraordinary happens when you travel at such tremendous speeds. Time itself begins to behave differently. This isn't science fiction or imagination. It's one of the most profound discoveries in the history of science, revealed to us by Albert Einstein over a century ago. As these satellites rush through the cosmos, time moves more slowly for them than it does for you. Lying still in your earthbound bedroom, picture yourself on the fastest train you imagine, racing through the countryside at impossible speeds. From your window, you watch the landscape blur past, but to you, inside the train, everything feels normal. Your watch ticks at its usual pace, your thoughts flow at their regular rhythm. But to someone standing on the platform, if you flash past, something remarkable would be happening, as they could somehow observe your watch. They would see it ticking slightly slower than their own timepiece. This is the strange and beautiful reality of Einstein's special theory of relativity. Time is not the same everywhere in the universe. It flows like a river, but a river that moves at different speeds depending on how fast you're moving through space. The faster you travel, the slower time moves for you relative to someone who is standing still. For the GPS satellites, racing through their cosmic orbits at tremendous velocity, this effect is small but measurable. Their atomic clocks, despite their incredible precision, run slightly slower than identical clocks here on Earth. If you could somehow compare their timekeeping to yours second by second, you would find that their clocks lose about 7 microseconds each day due to their high speed. 7 microseconds, such a tiny amount that you would need special instruments even to detect it. But here's where the poetry of physics reveals itself in unexpected ways. While the satellite's speed makes their clocks run slower, there's another force at work that makes them run faster. The satellites orbit so high above Earth that gravity's pull on them is weaker than what you feel lying in your bed. And in Einstein's universe, weaker gravity makes time flow more quickly. Imagine gravity as a gentle hand pressing down on the flow of time. Here on Earth's surface, that hand presses firmly, making time move at the pace you're accustomed to. But high above, where the satellites live, gravity's touch is lighter, allowing time to flow more freely. This effect causes the satellite clocks to gain about 45 microseconds each day compared to earthbound timepieces. These two effects, the slowing due to speed and the speeding due to weaker gravity, work in opposite directions, like cosmic forces playing tug-of-war with time itself. The gravity effect wins, being stronger than the speed effect, so the satellite clocks ultimately run faster than Earth-based clocks by about 38 microseconds each day. 30-8 microseconds might seem insignificant, hardly worth mentioning as you drift towards sleep, but in the world of GPS, where signals travel at the speed of light and distances are measured by the time it takes light to journey from space to Earth, this tiny difference becomes enormous. Light travels 300 million meters every second, which means it travels about 300 meters, the length of 3 football fields, in just 1 microsecond. If GPS ignored Einstein's discovery, if it pretended that time flows the same everywhere, the system would accumulate errors of about 10 kilometers each day. Within a week, your GPS would be so confused that it might tell you you're in a completely different city. The satellite racing overhead would announce your location based on its own perception of time, which runs slightly faster than yours, creating a mismatch that grows larger with each passing hour. But the engineers who designed GPS understood Einstein's insights. They programmed the system to account for these relativistic effects, adjusting the satellite clocks so that time stays synchronized between space and Earth. It's a constant dance of correction, a mathematical choreography that ensures the cosmic timepieces and earthbound clocks can work together in harmony. As you lie in the darkness, breathing slowly and deeply, consider the invisible adjustments happening above you every moment. The satellites race through their orbits, their atomic clocks ticking away the microseconds, while computer systems continuously compare these space-based timepieces with clocks on the ground. When tiny discrepancies appear, And they always do, because Einstein's universe demands it. The system makes delicate corrections, keeping the whole network synchronized. This is perhaps one of the most beautiful examples of how abstract physics becomes practical technology. Einstein developed his theories not to improve navigation, but to understand the fundamental nature of space and time itself. He was exploring the deepest questions about reality. What is time? How does motion affect the flow of temporal experience? What happens when gravity bends the fabric of space-time? Yet his insights, born from pure curiosity about the universe, now guide you home from work, help emergency responders find accident victims, and enable farmers to plant crops with precision. The same equations that revealed the cosmic dance of space and time now help you find a parking spot or meet a friend at a cafe. The satellites continue their eternal race, carrying with them not just radio transmitters and atomic clocks, but the practical wisdom of Einstein's greatest discoveries. They are messengers of relativity, broadcasting the news that time is not what it seems, that the universe is stranger and more wonderful than everyday experience suggests. Each time you check your location on a map or follow turn-by-turn directions, you're witnessing the marriage of cosmic physics and human ingenuity. The satellites adjust their sense of time to match yours, compensating for effects that exist only because we live in Einstein's universe rather than the simpler world Newton imagined. As the night deepens around you and your breathing grows more rhythmic, the satellites race onward through the darkness, their relativistic dance continuing while you rest. They carry with them the proof that our universe operates according to principles more elegant and surprising than any story ever told. But even with Einstein's adjustments accounted for, the satellites face countless tiny influences that threaten to disturb their perfect timekeeping, requiring an endless symphony of mathematical corrections that play out silently in the space above your dreams. In the quiet darkness above you, an invisible symphony of numbers flows between earth and sky. While you rest in your bed, mathematical equations work tirelessly to keep the world connected, correcting tiny errors and adjusting for influences so subtle that only the most sophisticated calculations can detect them. These numbers are poetry, written in the language of physics, gentle corrections that ensure tomorrow's journey will begin exactly where tonight's rest ends. The GPS satellites, racing through their cosmic orbits, face countless small disturbances that would gradually pull their signals out of tune, like a violin string that slowly loosens as it's played. The satellite system requires constant adjustment to maintain its perfect pitch. The atmosphere pushes against the satellites with solar wind, particles streaming from our sun that exert pressure as gentle as a whisper, but as persistent as time itself. Picture the satellites as ships sailing through an ocean of near-nothingness, where even the faintest current matters. Solar radiation pressure nudges them slightly off course, like a breeze that barely ruffles your hair, but can, over hours and days, push a satellite meters away from its intended path. The gravitational pull of the moon tugs at them with invisible hands, creating tides in their orbits just as it creates tides in our oceans. Earth itself is not the perfect sphere we might imagine. Our planet bulges slightly at the equator, like a spinning ball of clay that's stretched by its own rotation. This subtle asymmetry creates variations in gravitational pull that the satellites feel as they pass overhead. When they orbit above the equatorial bulge, gravity pulls them slightly stronger. When they pass over the poles, the pull weakens. These variations, measured in parts per million, still affect satellite timing with enough precision to matter. In the delicate dance of navigation, but perhaps most poetically, the satellites must account for the very air you breathe. The Earth's atmosphere extends far higher than you might expect, reaching up like invisible fingers to touch even these high-flying spacecraft. Though the air at satellite altitude is thinner than the best vacuum we can create on Earth, it still creates a whisper of drag that gradually slows the satellites down. The ionosphere, that layer of charged particles high above the clouds, acts like a cosmic lens that bends and delays the GPS signals as They travel from space to your device. During the day, when the sun energizes these particles, the ionosphere becomes more active, delaying signals by different amounts depending on their frequency. At night, as the ionosphere calms and the charged particles settle, the delays change, requiring constant mathematical adjustment. Water vapor in the atmosphere below also plays its part in this cosmic calculation. The invisible moisture in the air, the same humidity that might make a summer evening feel heavy, slows down GPS signals by a tiny fraction. Weather systems moving across continents create pockets of varying humidity that the satellites must account for, like a musician adjusting their instrument as the concert hall's temperature changes. All of these influences, solar pressure, gravitational variations, atmospheric drag, ionospheric delays, and tropospheric effects, would seem impossibly complex to track and correct if we tried to do it by hand. But mathematical algorithms, running continuously on computers both in space and on the ground, monitor these effects and make corrections with elegant precision. The mathematics involved is breathtakingly beautiful in its complexity. Equations flow through computer systems like water through carefully designed channels, each calculation building upon the last. Kalman filters, named after their inventor, sift through noisy measurements to extract the pure signal of satellite position and timing. These filters work like mathematical ears that can hear a whispered conversation in a crowded room, separating the important information from the background noise. Orbital mechanics calculations predict where each satellite should be at any given moment, accounting for the gravitational pull of Earth, Moon, and Sun. These equations, first developed to understand planetary motion, now guide artificial moons in their precise paths around our world. The same mathematical principles that helped us understand how Earth orbits the Sun now ensure that satellites orbit Earth with clockwork precision. Atmospheric models, built from millions of weather observations and physics-based predictions, estimate how the air will affect GPS signals hour by hour. These models digest information from weather balloons, ground-based sensors, and other satellites to create a three-dimensional picture of atmospheric conditions that changes constantly as weather patterns move across the globe. The corrections happen in layers, like a gentle adjustment of a musical instrument before each performance. Course corrections account for the major effects: orbital drift, atmospheric delays, and clock errors. Fine corrections address the subtle influences: solar pressure variations, gravitational anomalies, and ionospheric fluctuations. Ultrafine corrections polish the signal to perfection, accounting for effects so small that they exist at the very edge of what our instruments can measure. All of this mathematical choreography happens invisibly, silently, while you sleep. Ground stations around the world continuously monitor the satellites, comparing their actual positions and timing against predictions. When small discrepancies appear, and they always do, because the universe is full of subtle influences we're still learning to understand, the system calculates new corrections and uploads them to the satellites. The satellites receive these updates like musicians receiving new sheet music, adjusting their broadcast signals to account for the latest measurements and predictions. They modify their timing signals, update their orbital position data, and refine their atmospheric correction models, all while maintaining the constant broadcast of navigation signals that will guide tomorrow's travelers. Perhaps the most remarkable aspect of this mathematical symphony is its transparency to those who benefit from it. When you use GPS to find a restaurant or navigate to a friend's house, you never see the equations running in the background. The corrections happen seamlessly, invisibly, like the automatic adjustments your eyes make as they focus on different distances. The mathematics of GPS represents one of humanity's most elegant achievements, the creation of a system so sophisticated that it can account for effects predicted by Einstein's relativity, Newton's orbital mechanics, and modern atmospheric physics, all while presenting users with a simple, reliable service that feels almost magical in its accuracy as you sink deeper into sleep. The mathematical lullaby continues playing above you. Numbers dance through space-based computers. Algorithms adjust for atmospheric conditions, and correction factors flow between Earth and satellite in an endless stream of computational poetry. These equations, invisible and silent, keep our world precisely connected, ensuring that no matter how far you travel tomorrow, you'll always be able to find your way home to the exact place where you're resting tonight. The mathematics of wonder works while you dream, proof that some of the universe's most beautiful truths are written in the language of numbers, equations that sing the cosmos into perfect harmony. Right now, as you hold your phone, you're cradling one of humanity's most elegant achievements, a device that quietly performs miracles Einstein could only dream of. Within that familiar rectangle lies technology that speaks directly with the stars, or rather, with the constellation of satellites that orbit high above our heads like mechanical angels, each one carrying the gift of perfect time and precise location. Your phone doesn't simply receive signals from these orbital messengers. It engages in a sophisticated conversation, a cosmic dialogue that happens faster than thought itself. 24 satellites circle Earth twice daily, each one broadcasting its own story of time and space. But here's where the magic truly begins. These satellites experience time differently than you do, living in Einstein's realm, where gravity's grip is weaker and time flows just a little faster. Imagine each satellite as a cosmic storyteller, whispering its tale of where it is and when it believes that moment to be. Your phone listens to at least 4 of these storytellers simultaneously, gathering their individual narratives of time and position. But these stories arrive with a peculiar twist each. The light's clock runs slightly fast compared to earthbound time, gaining about 38 microseconds each day due to the weaker gravitational field in which they float. Your phone has been taught to understand this temporal language. Deep within its circuits lies the wisdom of relativity, algorithms that automatically translate the satellite's hurried time into your own slower, earthbound rhythm. It's as if your phone serves as a universal translator between 2 different experiences of reality, the satellite's accelerated time high above, and your own gravity-slowed time down here on the surface. When you ask your phone for directions, you're actually requesting it to solve one of the universe's most beautiful puzzles. Each satellite signal arrives at your phone having traveled a slightly different path through space and time. These signals carry timestamps that your phone must carefully decode, accounting for the fact that each satellite's clock ticks just a bit faster than your own. The mathematics happening in your palm involves the same equations Einstein used to describe the fabric of spacetime itself. Consider the delicate precision required for this cosmic conversation. Your phone must measure the time it takes for each signal to travel from satellite to Earth, calculating distances accurate to within a few meters. But if it ignored relativity, if it treated all clocks as running at the same rate, your location would drift by about 7 miles each day. The satellites would seem to disagree about where you are, their stories becoming increasingly contradictory as Earth's gravity tugged at time itself. Your phone performs this correction automatically, seamlessly, thousands of times each day. Every time you check your location, request directions, or simply allow an app to know where you are, your device is quietly consulting Einstein's theories. It's solving relativistic equations that would have amazed physicists just a few decades ago, treating the warping of spacetime as just another piece of data to process. The signals your phone receives have traveled roughly 12,000 miles through the vacuum of space, carrying their precise temporal messages at the speed of light. Each signal extraordinarily weak. By the time it reaches you, weaker than the light from a birthday candle viewed from 20 miles away. Yet your phone's antenna catches these whispers from space, amplifies them, and decodes their temporal secrets with remarkable accuracy. Think about the layers of translation happening in real time. The satellites broadcast in their own temporal reference frame, where time moves differently than it does for you. Your phone receives these signals in your earthbound reference frame, where gravity has slowed time's passage just enough to matter. The device then translates between these two experiences of time, finding the common ground where accurate positioning becomes possible. This translation happens so smoothly that you never notice it. You simply tap your screen and ask for directions to a restaurant, unaware that your phone is consulting the fundamental structure of the universe to answer your question. The same theories that describe black holes and the expansion of the cosmos are quietly working to help you navigate a dinner. Your phone doesn't just use relativity, it embodies it. Every GPS calculation is a small proof of Einstein's insights, a practical demonstration that time and space are woven together in ways that affect even the most mundane aspects of our daily lives. The device in your pocket carries the accumulated wisdom of decades of physics research, all focused on the simple goal of telling you where you are and how to get where you're going. As you drift towards sleep tonight, your phone continues its cosmic conversation. Even in airplane mode, even when you're not actively using GPS, the satellites continue their orbital dance overhead, broadcasting their stories of time and space to anyone who cares to listen. They're part of an invisible infrastructure of precision that spans the globe, a network of temporal perfection that makes modern life possible. The next time you glance at your phone's map, remember that you're looking at the visible result of an invisible miracle. Einstein's theories translated into practical help, relativity transformed into navigation, the universe's deepest truths condensed into turn-by-turn directions. Your phone is more than a communication device. It's a window into the fundamental nature of reality itself. But your phone is just one listener in a much larger conversation. Across the Earth, thousands of other devices and systems are engaged in the same cosmic dialogue, creating an intricate web of precision that spans continents and connects every corner of our planet through the shared language of perfectly synchronized time. While you sleep peacefully in your bed, an invisible network of extraordinary precision continues its quiet work around the world. Imagine, if you will, a constellation of listening posts scattered across every continent, from the Arctic tundra to tropical islands, from bustling cities to remote deserts. Each station stands as a sentinel of time, constantly monitoring the satellite signals that make your GPS work, ensuring that the cosmic conversation between Earth and space remains perfectly tuned. These monitoring stations are the unsung guardians of global positioning, tracking every satellite in the GPS constellation with the devotion of astronomers watching distant stars. But unlike astronomers seeking to understand the cosmos, these stations have a more practical mission. They listen to each satellite's story of time and location, checking for any subtle drift or inconsistency that might disrupt the invisible web of precision we all depend upon. Each monitoring station houses atomic clocks, devices so precise they would lose less than 1 second if they ran for millions of years. These earthbound timepieces serve as the ultimate reference, the golden standard against which all satellite clocks are measured. They tick with mechanical meditation, their cesium atoms vibrating exactly 9,192,630,1,770 times each second, defining the very nature of time itself through their quantum rhythm. The stations don't simply listen. They engage in a continuous dialogue with the satellites overhead. They track each satellite's orbit with extraordinary precision, noting tiny perturbations caused by the moon's gravity, the sun's radiation pressure, even the slight oblateness of Earth itself. They measure how the satellite clocks drift compared to their own atomic standards, calculating corrections that maintain the system's remarkable accuracy. Think of these stations as conductors of a global orchestra, each one listening to the satellite choir and making tiny adjustments to keep the cosmic symphony in perfect harmony. When a satellite's clock begins to drift perhaps by a few billionths of a second, the monitoring stations detect this subtle change and relay the information to the master control station, where corrections are calculated and uploaded back to the wayward satellite. This correction process happens continuously, 24 hours a day, 7 days a week. The monitoring stations never sleep, never take breaks, never stop listening to the satellite signals that cross the sky above them. They form an invisible safety net of precision, catching any temporal imperfection before it can affect the millions of GPS users around the world. The Master Control Station, nestled in Colorado Springs, serves as the brain of this global network. Here, data from all the monitoring stations converges, creating a comprehensive picture of the entire GPS constellation's health and accuracy. Specialists analyze orbital mechanics and relativistic effects with the same care that a doctor might monitor a patient's vital signs, ensuring that each satellite maintains its proper position in both space and time. From this central hub, corrections flow back to the satellites through a network of ground antennas. These updates arrive as streams of data, telling each satellite exactly how much its clock has drifted and providing updated information about its precise orbital position. The satellites receive these corrections like students accepting gentle guidance from wise teachers, adjusting their internal understanding of time and space to maintain the system's overall accuracy. But the network extends far beyond the official GPS monitoring stations. Around the world, thousands of other systems contribute to this web of precision. Survey markers embedded in bedrock serve as fixed reference points, their positions known to within millimeters. Scientific instruments scattered across the globe, from earthquake monitors to weather stations, depend on GPS timing so precise that they effectively become part of the monitoring network themselves. Radio telescopes occasionally join this cosmic conversation, using their enormous dishes to listen for the faint GPS signals and verify their accuracy against the backdrop of distant quasars. These astronomical observations help scientists understand how Earth's atmosphere affects satellite signals, leading to better correction algorithms and improved accuracy for everyone. The invisible network even extends beneath the oceans, where underwater cables carry timing signals between continents, synchronizing atomic clocks separated by thousands of miles. These submarine connections ensure that the global network of precision remains connected even when satellite signals are blocked or disrupted, creating redundant pathways for the flow of perfect time. Research stations in Antarctica contribute their own unique perspective to this global network, monitoring GPS signals from the bottom of the world where the aurora borealis can interfere with satellite communications. Their observations help scientists understand how solar activity affects the precision of GPS, leading to better predictions and more reliable service for users everywhere. Each monitoring station, each atomic clock, each correction algorithm represents a small victory over the chaos of natural imprecision. Together, they create something remarkable, a global infrastructure of time that allows a farmer in Kansas to guide his tractor with centimeter accuracy, enables a ship captain in the Pacific to navigate safely through fog, and helps emergency responders find people in need anywhere on Earth. The beauty of this network lies not just in its technical precision, but in its quiet invisibility. Most people never think about the monitoring stations that make their GPS work, never consider the atomic clocks that tick away in remote facilities, never wonder about the constant stream of corrections flowing between Earth and space. The network succeeds because it remains hidden, working flawlessly behind the scenes to support the visible world of maps and navigation. As you rest tonight, this invisible web of precision continues its patient work. Monitoring stations listen to their satellite songs, atomic clocks tick their quantum rhythms, and correction signals flow upward through the darkness toward the constellation of navigation satellites that will guide tomorrow's travelers safely to their destinations. But what would happen if this carefully maintained precision suddenly disappeared? What if Einstein's insights about time and gravity were somehow wrong, and the delicate corrections that keep GPS working simply stopped working? Let us drift together into a world of gentle impossibility, a thought experiment that illuminates the invisible foundations of our modern life. Imagine, for a moment, that Einstein had been mistaken about the nature of time and gravity. Picture a universe where time flows uniformly everywhere, where gravity doesn't slow clocks, where the satellites orbiting overhead experience exactly the same temporal rhythm as you do here on Earth's surface. In this alternative reality, GPS would have seemed like a brilliant idea at first. Engineers would have launched their constellation of satellites with great confidence, expecting the system to work exactly as designed. The satellites would broadcast their timing signals with mechanical precision, and GPS receivers would calculate positions using the simple assumption that all clocks, everywhere, tick at the same rate. For the first day, everything would appear normal. Your phone would confidently announce your location, seemingly accurate to within a few meters. Travelers would follow their GPS directions with trust, ships would navigate by satellite signals, and pilots would rely on space-based positioning for their approaches to busy airports. The world would celebrate this technological triumph, unaware of the subtle error growing within the system. But by the second day, careful observers would notice something troubling. GPS positions would begin to drift slightly, showing locations that were off by a few dozen meters. At first, these errors might be dismissed as temporary glitches, the kind of minor imprecision that all technology occasionally exhibits. Engineers would check their calculations, update their software, and assume the problems would resolve themselves. By the end of the first week, the errors would grow impossible to ignore. GPS receivers would show positions off by hundreds of meters, then kilometers. The satellites, running on clocks that actually tick faster than Earthbound time, would gradually lose synchronization with the ground-based systems that track them. Each satellite would drift into its own temporal isolation, broadcasting timing signals that made less and less sense when compared to the others. Imagine the growing confusion as this alternative GPS system degraded. Your phone's map would show you standing in the middle of a lake when you're actually driving down a highway. Emergency services would receive calls for help with locations that placed the caller miles from their actual position. Ships would find themselves apparently sailing through dry land according to their navigation systems, while their actual positions remained mysterious. The aviation industry would be among the first to abandon GPS entirely. Pilots, trained to trust their instruments, but also to recognize when those instruments lie, would notice the increasing unreliability of satellite navigation. They would return to older methods: radio beacons, celestial navigation, dead reckoning, anything more reliable than the temporally confused satellites overhead. Agricultural systems that depend on GPS for precision farming would begin to fail. Tractors guided by satellite signals would plow crooked furrows, plant seeds in overlapping patterns, and apply fertilizers with chaotic imprecision. The careful efficiency of modern farming would give way to the uncertainty of pre-GPS agriculture, reducing crop yields and increasing waste. Scientific research that depends on precise timing would become impossible. Earthquake monitoring networks would lose their ability to triangulate seismic events, making it difficult to understand where tremors originate or how they propagate through the Earth. Weather prediction would suffer as the precise timing needed to coordinate atmospheric measurements disappeared into temporal chaos. The financial markets, which depend on GPS-synchronized clocks for time-stamping transactions, would face unprecedented challenges. Trading systems would struggle to maintain fair order matching when different market participants operate on clocks that gradually drift apart. The microsecond precision that enables high-frequency trading would become impossible, forcing markets to slow down to accommodate the growing temporal uncertainty. Telecommunications networks would gradually degrade as cell towers lose their ability to synchronize with GPS timing. Phone calls would suffer from increasing delays and dropouts as different parts of the network fall out of temporal alignment. The Internet itself would become less reliable as data packets struggle to navigate networks where different routers operate on increasingly divergent clocks. Search and rescue operations would become exponentially more difficult. When someone activates an emergency beacon, rescue teams would receive location information that could be wrong by many miles. The golden hour that often means the difference between life and death would be consumed by the search for victims who aren't actually where their GPS coordinates suggest they should be. Surveying and construction would return to older, slower methods. Building sites would lose the precise positioning that enables modern construction techniques. Large projects that depend on millimeter-level accuracy would become impossible without GPS, forcing engineers to rediscover the careful techniques their predecessors used before satellite navigation existed. Even personal navigation would become an exercise in frustration. The confident blue dot on your phone's map would wander randomly, sometimes showing you miles from your actual location. Turn-by-turn directions would become meaningless when the system can't accurately determine where you are or where you're going. People would return to paper maps and written directions, skills that many had forgotten in the GPS age. As this alternative world struggled with its failing satellite navigation, scientists would eventually trace the problem to its source, the assumption that time flows uniformly everywhere. They would realize that the satellite's clocks run fast not because of any mechanical defect, but because they experience weaker gravity than Earth-bound clocks. The solution would require accepting a counterintuitive truth: time itself bends and flows differently depending on where you are in the universe. The engineers would face a choice: abandon GPS entirely, or embrace the strange insights of relativity. They would need to program their systems to expect satellite clocks to run fast, to automatically correct for the time dilation effects of both gravity and motion. They would need to accept that the universe operates according to principles that challenge our everyday intuition about the nature of time and space. In our real world, Einstein was right, and GPS works because we've built relativistic corrections into every calculation. The satellite's clocks do run fast, exactly as Einstein predicted they would. The system succeeds because we've embraced the counterintuitive nature of time itself, programming our technology to work with the universe's actual behavior rather than fighting against it. As you settle deeper into comfort tonight, you can rest easy knowing that Einstein's insights continue to serve you faithfully, ensuring that the GPS in your pocket will accurately guide you wherever you need to go. The alternative world we've imagined, a world without working GPS, helps us appreciate the invisible miracle of relativity quietly working in our everyday lives. As you begin to drift toward the gentle shores of sleep, let your mind wander through the quiet poetry of how Einstein's most abstract insights have woven themselves into the fabric of ordinary life. This is not the relativity of textbooks and equations, but the lived relativity that touches every moment of your day with invisible hands, guiding and protecting in ways you might never notice. Consider how your morning begins. Before you're fully awake, your phone has already engaged in its cosmic conversation with the satellites overhead, determining your precise location while you sleep. When you first glance at your weather app, checking to see if you need an umbrella, you're consulting information that arrived through a network synchronized by GPS timing. The meteorologists who predicted today's weather rely on atmospheric sensors scattered across the globe, each one coordinated by satellite signals that carry the whispered corrections of relativity. Your morning commute unfolds as a gentle demonstration of space-time geometry made practical. When you ask for directions to work, your phone doesn't simply calculate the shortest distance between 2 points. It consults real-time traffic data gathered from millions of other GPS-enabled devices, creating a dynamic map of human movement that updates faster than thought itself. Each traffic jam, each accident, each construction delay becomes part of a vast information network that helps you navigate not just through space, but through time, finding routes that minimize not distance, but duration. The buses and trains that carry commuters to work operate on schedules synchronized by GPS timing, their arrival predictions accurate to the minute, because satellites overhead provide a universal reference for time itself. When a train system announces that the next departure is in 3 minutes, that precision comes from atomic clocks in space. They're relativistic corrections ensuring that 3 minutes means the same thing whether you're waiting on the platform or riding in the conductor's cabin. Emergency services live and breathe by GPS precision in ways that can mean the difference between life and death. When someone calls for help, dispatchers don't just need to know the general neighborhood, they need to pinpoint the exact building, the precise apartment, sometimes even the specific room where assistance is needed. The GPS coordinates that appear on emergency dispatch screens carry Einstein's corrections, ensuring that ambulances, fire trucks, and police cars arrive at the right location rather than wandering through nearby streets. Search and rescue operations depend on this precision. Even more critically, when hikers become lost in wilderness areas, when boaters find themselves in distress far from shore, when pilots need to make emergency landings in remote locations, GPS provides the exact coordinates that guide rescue teams through the darkness. Every successful rescue is a small victory for relativity, a practical application of theoretical physics that brings people safely home. The delivery trucks that bring packages to your door navigate using GPS systems that must account for relativistic effects thousands of times each day. The efficiency of modern logistics, their ability to track packages from warehouse to doorstep, to optimize delivery routes that save fuel and time, to coordinate the complex dance of global commerce depends on satellite navigation accurate enough to distinguish between neighboring houses on the same street. Agricultural systems have embraced GPS with remarkable precision, using satellite guidance to plant seeds in perfectly straight rows, to apply fertilizers and pesticides with minimal waste, to harvest crops with maximum efficiency. Farmers working 1,000-acre fields rely on GPS accuracy measured in centimeters, using the universe's most sophisticated physics to grow the food that feeds the world. The wheat in your morning toast, the corn that feeds the cattle that provide your milk, the soybeans that create countless products, all grown with the assistance of Einstein's insights about the nature of time and space. Financial markets operate at speeds that make GPS timing essential for fairness and accuracy. When stock trades are executed in microseconds, when different market participants must compete on equal temporal footing, synchronized clocks become crucial for maintaining market integrity. The timestamp on every financial transaction carries the invisible signature of relativistic corrections, ensuring that time flows uniformly across trading floors, separated by thousands of miles. Scientific research has embraced GPS timing for applications Einstein never could have imagined. Earthquake monitoring networks use GPS signals to detect ground movements measured in millimeters, providing early warning systems that protect communities from seismic disasters. Climate researchers use GPS to measure tiny changes in sea level, tracking the effects of global warming with unprecedented precision. Biologists studying animal migration attach GPS collars to wildlife, following the movements of species across continents and seasons. Even entertainment and social connection rely on GPS in subtle ways. When you share your location with friends, when you tag photos with geographic information, when you find nearby restaurants or discover local events, you're participating in a location-aware world made possible by relativistic corrections flowing invisibly through satellite networks. The social fabric of modern life has become interwoven with precise positioning, creating new forms of community and connection based on shared physical space. The power grid that lights your home and charges your devices depends on GPS for synchronization. Across vast networks, electrical generators separated by hundreds of miles must coordinate their output to maintain stable power delivery. And this coordination requires timing precision that only GPS can provide. The lights that illuminate your evening, the refrigerator that keeps your food fresh, the computer that connects you to the world all depend on a power grid synchronized by satellites overhead. Consider the profound irony that some of the most abstract concepts in physics, ideas about the nature of time and space that challenged humanity's deepest intuitions about reality, have become essential infrastructure for practical daily life. Einstein's thought experiments about riding alongside light beams have evolved into turn-by-turn directions that help you navigate unfamiliar neighborhoods. His insights about gravity's effect on time have become the invisible foundation for emergency services that save lives every day. This is the quiet poetry of applied physics. Theoretical insights so profound they seem to exist in a realm completely separate from ordinary experience have become the hidden scaffolding that supports modern civilization. Relativity doesn't just describe the universe, it serves the universe, working tirelessly behind the scenes to keep us connected, safe, and precisely positioned in both space and time. As you rest tonight, Einstein's revelations continue their patient work. Satellites orbit overhead, their clocks running fast in their weakened gravitational fields, broadcasting signals that carry the temporal corrections needed to maintain GPS accuracy. The same forces that govern black holes and expanding galaxies also guide the delivery driver who brings your packages, the emergency responder who answers calls for help, and the navigation system that helps travelers find their way home. The universe's deepest truths have become our most practical tools, and in that transformation, we find a kind of cosmic poetry that connects the abstract beauty of theoretical physics to the concrete needs of human life. But as practical as GPS has become, it remains fundamentally a conversation between Earth and space, a dialogue that continues even as we sleep, guided by forces larger and more mysterious than our daily concerns. Above you, as you settle into the deepening embrace of sleep, 24 satellites continue their ancient dance around Earth, each one a mechanical moon, carrying the gift of precise time through the darkness. They orbit in paths so carefully calculated that they seem to follow invisible rails through space, their movements as predictable as clockwork, as reliable as the rising sun, as constant as the gentle rhythm of your breathing. These silent companions travel at speeds that would carry them from New York to Los Angeles in 10 minutes. Yet they maintain their orbital positions with such precision that ground controllers can predict their locations years in advance. They are both incredibly fast and perfectly stable, racing through space while remaining exactly where they need to be, when they need to be there. Like the most devoted friends, they are always available when you need them, always ready to help you find your way. Each satellite carries atomic clocks that tick with the rhythm of quantum mechanics itself, counting the vibrations of cesium atoms with metronomic precision. These clocks represent humanity's most accurate timepieces, yet they run slightly fast in their high orbital homes where gravity's pull is gentler than it is down here where you rest. This tiny difference, barely 38 microseconds per day, would seem insignificant in any other context, but in the delicate mathematics of positioning, it becomes the key to everything. The correction signals that adjust for this temporal difference flow upward from Earth like invisible prayers, carrying the accumulated wisdom of Einstein's insights into the realm where satellites dwell. These corrections are love letters, written in the language of physics, messages that say, "We understand that time flows differently for you up there, and we've learned to translate between your experience and ours." The satellites receive these corrections with the electronic gratitude, adjusting their internal understanding of time to maintain their service to the world below. Think of the profound trust embedded in this system. Every day, millions of people place their faith in calculations that depend on accepting the counterintuitive truth that time itself can flow at different rates. Parents driving children to school, pilots guiding passengers across oceans, emergency responders racing to save lives, all trust in technology that works only because we've embraced ideas that challenge our deepest intuitions about reality. The GPS constellation forms a gentle cage of precision around our planet, not a prison, but a protective embrace that keeps us connected to each other and to the places we need to be. These satellites ask nothing from us except the opportunity to serve, broadcasting their signals freely to anyone who wishes to listen. They play no favorites, judge no destinations, simply offer their gift of guidance to anyone with a receiver, capable of hearing their electronic whispers. as you drift deeper into sleep. Your phone rests quietly beside you, its GPS receivers still engaged in its cosmic conversation even as you dream. The satellites continue to broadcast their stories of time and location, and your phone continues to listen, maintaining an awareness of your position even as your consciousness travels to places no satellite could ever track. In sleep, you journey through landscapes of memory and imagination, while your physical body remains precisely positioned in space and time. The monitoring stations scattered across the globe continue their patient vigil, their operators working through the night to ensure that the satellite constellation maintains its accuracy. In control rooms filled with softly glowing screens, technicians watch over orbital mechanics and atomic clocks with the dedication of shepherds tending their flocks. They are the guardians of global positioning, ensuring that tomorrow's travelers will find the same reliable guidance that served today's journeys. Consider the beautiful irony that some of our most restful moments are supported by technology that never rests. While you sleep, satellites continue their orbital dance, atomic clocks continue their quantum counting, monitoring stations continue their careful listening, and correction signals continue their upward flow. The infrastructure of precision operates with tireless devotion, creating a foundation of reliability that allows you to rest deeply, knowing that the world's navigation systems will be ready when you need them. The same mathematical principles that describe the curvature of spacetime around massive objects also ensure that your morning commute will be guided by accurate directions. The same relativistic effects that govern the behavior of matter near black holes also help emergency responders find people in need. The same insights that revealed the fundamental nature of time and space also power the everyday miracles of modern navigation. There is something deeply comforting about resting beneath this constellation of mechanical precision, knowing that the universe's most sophisticated physics works quietly to serve humanity's most basic needs. The satellites overhead represent our species' growing understanding of cosmic forces, transformed into practical tools that help us find our way through the complexity of modern life. As your breathing slows and your mind begins to wander through the first stages of dream, the GPS satellites continue their eternal orbits, carrying their atomic clocks through the darkness like mechanical fireflies, each one broadcasting its message of time and location to the sleeping world below. They are patient guardians of precision, content to serve without recognition, happy to guide without fanfare. The invisible web of positioning and timing that spans our planet will continue its work through the night, maintaining the connections that hold our technological civilization together. Power grids will remain synchronized, communication networks will stay coordinated, and navigation systems will preserve their accuracy, all sustained by the gentle flow of perfectly measured time from space to Earth. Rest now in the knowledge that Einstein's insights about the nature of reality continue to serve you faithfully, that the universe's deepest truths work tirelessly to keep you connected and safe. The satellites overhead will watch over your sleep like benevolent stars, their atomic clocks ticking away the hours until morning brings new journeys and new destinations to discover. Sleep well, knowing that when you wake, the same forces that govern galaxies and guide light through curved spacetime will be ready to help you navigate whatever path you choose to follow. The cosmic conversation between Earth and space continues, and you are part of its beautiful, ongoing story.